Well, so far, this unit has been pretty dismal. We introduced the I model, where everybody gets sick. Not only does everybody get sick, it grows exponentially. And hopefully, you learned in looking studying the last packet, you get more than 100% of the population sick after a while, which is why the model clearly can't be right. So it's a model that works early on as a model, but once we have a significant proportion of the population being infected, it just doesn't work anymore. But it's really morbid in that, more than 100% of the people will end up getting sick. So that one is really depressing. Then we had a model that seemed a little more realistic and was a little less depressing, the SI model, where after a while people start getting sick less quickly because there just aren't as many people around who haven't yet been infected. So it's still depressing though, because everyone gets sick. We just don't have it growing exponentially forever. So it slows down and people the sickness begins to trickle in after a while. But in the end, we're asymptotically approaching the point where everyone gets sick, and it's really depressing. But I have some good news for you. We have another model. The next model we want to look at is the SIR model, and it provides us some hope. In fact, it makes me happy, which is why I changed into my Hawaiian shirt. In this model, people can recover. So life gets better because the susceptible people can get infected, but infected people can recover or be removed from the pool of people who have infections. So let's explore this model, which has a lot more hope to it. Okay, so in the SIR model, we have the S's. Hopefully you remember that those are the susceptible people, the people who could get sick. We have the infectious. That's the I part of the model. But now we will have the removed. Okay, so how do people get removed? Well, first of all, let's follow the flow of this. So what's going to happen is susceptible people can become infected, right? But in this model, we can go one step further. The infected people can become removed. So what is the way that they can become removed? Okay, they can become immune. So if you had chicken pox when you were little, you're not going to catch chicken pox when you're older, for the most part. There are a few exceptions, but usually once you've had chicken pox, you're immune to getting chicken pox. So getting chicken pox as a kid is not always a bad thing. Now there's a more morbid reason you might be removed from being infectious, and that's because you die. All right, so we do want to avoid that, but the positive thing, the bright cheery thing, is that people can become immune to the disease that's going around. Okay, so that is the upside of this. All right, now this is actually a pretty easy change that we can make to our model. The mathematics of the solution become very complicated, but we'll let MATLAB take care of that for us. So once again, let's focus in on what happens on the infection side of things, DI, DT. So we want to know how fast will the infections increase? Okay, what is the rate at which the infections are growing? And we can start with our model from before, that we take a constant times the number of people who are infected times the number of people who are susceptible to being infected. All right, so this follows the old model. You have to start with a few people being infected, or you won't have an epidemic at all. If no one's sick, the susceptible people will never catch anything. So let's start with that. Okay, then we can take away the people who are being removed. Now this is the hard part. Okay, so the first term is the AIS term, but then people must be removed. Okay, so let's have another constant B. Okay, so we'll have a B in here. But what determines how many people can be removed? Some constant factor, but people can only be removed from the infected pool. So the more people who are infected, the more people can be removed. If 10 people have the chicken pox and they recover, you can only remove 10 people from the infection pool. But if there are 1,000,000 people with chicken pox, obviously we can remove a lot more people from the infection pool. Doesn't matter how many were susceptible. To be removed, you had to go through the infection at this point of our model. So we simply take minus b times I. Okay? So this is the key differential equation. It's a differential equation because it has a derivative in it, but it has some implications. We know that the total population doesn't change. We'll include those who have died as still part of the population. So we know, we're going to see this, that S plus I plus R will equal 1, which is 100% of the population. But over here, we could write dr dt. The rate at which people are being removed from the infection pool is going to, in order to keep the total the same, must be positive BI. So the BIs are moving out of the infection pool, hence minus BI. If I look at this equation, it's minus BI because you're moving away from being infected, but it's plus BI in the removed pool because those are the people being added to the removed pool, all right? And likewise, with the AIS, it's positive in the infection pool because the AIS is moving into the infected pool, but it's moving out of the susceptible pool. So I could write that ds dt is equal to negative AIS because AIS is moving out of susceptible and into infected, and BI is moving out of the infected and into the removed pool. And then we have our equation S plus I plus R equals 1. So we could easily, once again, say that rather than working with all three differential equations, we could find S by simply taking 1 minus I minus R. All right. Now, let's consider what happens in the case that some of these values are changing. So let's look at actually 3 different phases of what could be happening. So in phase 1, this is when S is almost the entire population. It's just barely less than 1. So we could almost call it 1. I will be small. A few people are going to come into the healthy population with the infection, so I will be very small. And no one has recovered because no one has had time to get sick yet. The few people who maybe were infected have not yet moved out of the infected pool to the recovered pool. So if we carefully look at the equation, di dt is equal to AIS minus BI. Since hardly anyone is infected yet, this is extremely small, very small. Now, I've said that I is small, but S is large. Okay, so A times I times S is actually reasonable size compared to BI. So what is the end result of that? That means this is almost equal to AIS, the first term. And if you remember, that's exactly what dIdt equaled for exponential growth. So this would give us exponential growth initially. Okay, so when we start out with a large, with nearly everyone being susceptible and a small number of infected people, we get exponential growth at first. All right, now let's move into phase 2. Okay, so in phase 2, as I grows, S will shrink. Okay, so that's the important thing. As more people become infected, there are fewer susceptible people. Remember, our boxes in the last example. So we're moving to the box where we have, we have a much larger number of infected people with the susceptible people. And at some point, let's look at this. So we have di dt is equal to AIS minus B times I. Okay, so let's look at this just with some arrows. Okay, so I is going up, but S is coming down. Whereas the second term simply has I going up. So A and B are constants, they're neither moving up or down. So as time progresses, the first term it may grow for a while. We saw that in the previous model. The first term may grow for a while, but then it may actually get smaller. Okay, so if you just look at the AIS, all right, we end up with with this growing. Oh, and by the way, in the last case, I should have said this, to make it exponential growth. It's exponential growth because the S is equal to 1. So it really is that you have AI. In this case, the first term is AIS. So remember, that would lead to growth that is logistic growth. All right. But DIDT, the slope of that growth curve reaches a maximum at some point and then starts getting smaller. So the second term, though, is only going to get bigger. Okay, so what happens is eventually this is the key, this eventually reaches 0. So phase 2 is kind of the time between where we start and when we have this, the DIDT equals 0. Now, what does that mean? If DIDT equals 0, hopefully you know from optimization problems, this means we either have a local maximum or local minimum. In this case, it is a local maximum because I was growing and the derivative going to 0 means that it will stop growing. We're going to see in phase 3 that it's going to go down. So that will, in fact, be a local maximum. That's a great thing. That's the great news right here. The number of people being infected is going to reach a peak. Okay. Now, it doesn't mean that new people aren't becoming infected. What it means is people are becoming infected. That's the first term, just as quickly as people are being removed from the infected pool. So we've reached an equilibrium. All right. So this is the equilibrium point. It's the number coming from S into I is going to be the same as the number that's leaving I into R. All right. Now, the good news is in phase 3, if we keep going with this, we changed to blue here. So phase 3, if you keep on going along, since S can do nothing but go down, di dt is equal to, again, A I S minus B I. So I, we learned, can go up or down. So let me write that up. I can go up or down possibly because we're removing people from I. But since S continually goes down over time, the first term, this must shrink. If I goes up, the only way it can do it is by pulling S down. So we've already reached the point where IS is optimized. So if we continue forward in time, even if I goes up, which it will, probably, or it could, the S must come down. So the rate will have passed the point where BI will exceed AIS. And so all of this is going to be negative, all right? This means the curve, the I versus T curve, must slope downward. So the number of infections is decreasing. Now, it doesn't mean, it's because people are leaving the infected pool and going to the removed pool. hopefully because they're now immune to the disease. So that's great news. We can actually have a cap to our I value. Hopefully that'll be much larger, or I'm sorry, much smaller than 1. We would like it to only be a small percentage of the population that is sick at a time, so that we don't overburden our hospitals. So we can hopefully do things that will make us hit that peak and go downward as soon as possible. The key factor, you may have guessed this, let me circle this in green, is this A, okay? That's the factor that we can change with good hygiene and social distancing. If we make that A smaller, we reach the peak sooner. The derivative, dIdt, will reach 0 sooner if A is smaller. And we'll have a quicker downward curve if A is smaller. So by practicing social distancing and good hygiene, we can hit the peak sooner, and we can, or I should say, at a lower infection rate, and we can cause it to go back down towards 0 much faster. So that would be our goal in controlling this infection.